is an associate professor in the Complex Systems group at the Department of Physics. He obtained his PhD from State University of New York at Stony Brook in 1993, and his areas of interest are statistical mechanics, quantum computing, Hamiltonian chaos, quantum chaos, and information. He's going to talk about generation of multipartite entanglement.
I'm extremely happy to be here and thank Professor Vishal Sani and other organizers for giving me this opportunity to be in this very interesting place and for the wonderful hospitality. I'm going to talk about some work. Some of the collaborators are here, but I will emphasize work primarily done somewhat more recently with undergraduate students from IIT Madras. These two guys, Karthik and Sharma, are pursuing their PhDs at these places. Shudodhan is still an undergraduate student there, and some work also with Satya Majumdar and Boigas were at Oxford. Okay, so that's the outline. I'll first introduce very briefly the notions of entanglement and its measures. And what I want to primarily consider is what happens to entanglement at avoided crossings of energy levels, because I think that's an important and interesting thing. And I will motivate that with this example Hamiltonian of spin chains. And we will basically consider how entanglement across many particles is generated. And towards that end, I would like to say a few things about entanglement in random states, and then go on to consider superpositions as a model of avoided crossings, and therefore consider some simple models of superpositions of many particle states. Dimerized states will be very simple states, simple in the sense of entanglement. They will be having very simple entanglement properties. And then we will superpose them with random states, which are like dirty states with very large entanglement content and very random things, and see what happens. We will also take very simple, both states to be very simple, like two dimerized states, and superpose them and see what happens. These are to develop intuitions about what happens at avoided crossings. Okay. So, very briefly, entanglement has already been talked about and has also been introduced in the morning. But if you have to reiterate, for example, if you have two classical bits, 0 and 1, you have only 4 possible states. But in quantum mechanics, superposition kicks in and you can have a 6-fold infinity of states, which are basically superpositions of all of these states. So, but then this also implies some very strange states, in the sense, for example, this spin singlet state, which we study in quantum mechanics in the first course. If you ask whether spin A is up or spin B is down, or whether it is to some other definite states, we can associate no such state. So this is the property of entanglement, and I think as far as pure states is concerned, Schrodinger in 35 said it all when he said that the whole is in a definite state, but the parts are not. So to generalize, if you have n particles, pure state is entangled if it cannot be written as an outer product of these things. That is, you cannot associate a definite state to these n particles. Again, it has already been introduced at the previous talk, some of these notions. Just to recapitulate, we have the simplest case of 2 particles, one of dimension n, another of dimension k, the Hilbert spaces. The product spaces of this dimension n into k, and any product state is written in terms of some product basis with n into k components. But if you ask what is the state of subsystem A, then you get by tracing out B, and that can be written in a form which is a manifestly positive matrix A dagger A, where A is this matrix of coefficients of this pure state. So rho is a positive operator, A dagger A, and rho B will be actually just A dagger. Or rho B is A dagger A, and rho A is A dagger. And therefore, they have the same spectrum. They have the same eigenvalues. They are positive eigenvalues. But because they are density matrices, they trace as 1. And it's now sort of accepted that a measure of entanglement in such bipartite states is the von Neumann entropy of these reduced density matrices, which you get from the eigenvalues of these reduced density matrices. And the maximum entropy of entanglement, or entropy, is the logarithm of the dimension of the smaller space. And that happens when all the eigenvalues are 1 over n for the reduced density matrix. And it's 0 when it's the case when only one eigenvalue is positive. In that case, it's separable. Going beyond 2, here we have a state with 3 qubits called a GHZ state after people who originated it and stated some of its remarkable properties. It's an interesting state in the sense that this is an entangled state. It cannot be written as a superposition. It cannot be written as a tensor product of 3 states belonging to each of the qubits. However, if you take a reduced density matrix of AB by tracing out C, it's easily done, you get this state. It's a mixed state. And this mixed state, although it looks kind of entangled, is actually not entangled, because it can be written as a convex combination like this, where this rho IA belongs to system A and rho IB belongs to system B. It's a convex combination with this PI being 1/2. If this is the case, then the interpretation is that the state can be created by A and B without talking to each other, or without actually quantum exchanging any kind of entanglement. So it can be locally created, so to speak, with just local operations in classical communication. And therefore, it is considered to be unentangled. In fact, it's unentangled. So any state that's written like this is unentangled. So the case of density matrix is slightly more complicated, actually much more complicated than that of pure states. So this is actually an unentangled state. So the GHZ state is such that, from the symmetry of this, you see that no 2 of these qubits are entangled. However, all 3 are entangled together. So this is a situation which is somewhat like the classical Borromean rings configuration, where you have 3 rings of which no 2 are linked to each other, but all 3 are linked together. So it's in a configuration, the entanglement is in a configuration which is like this. But also, as far as this talk is concerned, I would emphasize that there is no entanglement between any 2 of these qubits. Does not, of course, imply that the state doesn't have any entanglement. So if you have no pairwise entanglement, that doesn't mean that the state is not entangled. And in fact, it can be in a very entangled state like this GHZ state. There is a, if you were given a bipartite state which is mixed, so that it can be written in this form, where these are themselves probably entangled states, the entanglement of formation is defined as this minimization over all possible purifications of this density matrix like this, where this is the von Neumann entropy of this pure state. And there are an infinite number of ways of doing this in quantum mechanics, and that's what leads to the complication of this measure. But in the case when these are just 2 qubits, so there are 2 qubits in a mixed state, this problem was solved in 1998, 99, and there's a formula for a quantity called concurrence as defined by Hill and Hooters, which solved this problem of entanglement of formation. And d greater than 2, to my knowledge, is still an open problem. So let me just quickly define this measure due to Hooters, 97 apparently. So what we have in mind is two spin half particles in a mixed state, and they are in the state rho AB. Okay? So the prescription of Wooters goes as find this quantity rho AB, and this is the sigma y, the Pauli matrices, and the star operation here is important. So this is all done in the standard basis, and then this matrix combination is a 4 by 4 matrix. Find out its eigenvalues, arrange them in a decreasing order, and then you compare this combination with 0 and see whether it is positive. So if the CAB is positive, then that is the concurrence. Otherwise, it is 0. So it's a fairly involved prescription, not very transparent in what it is doing. For pure states, actually the situation is much simpler, but then we know how to measure it for the pure states. So I just want to emphasize that there is a well-known measure of entanglement for 2 qubits that can be calculated in principle. But now suppose you are not interested in just the entanglement between 2 qubits. You have many qubits in your state, and you're interested in characterizing entanglements of other kinds, multipartite entanglement. Now here comes a slew of measures. Some of the simplest measures are simply this. So this is the average purity of a single qubit. So this is the reduced density matrix of single qubit. You take the average purity of the single qubit. Okay. So this is called a Q measure, and it's also related to a tangle which was introduced by Wooters, but that's not essential for us. And another measure of multipartite entanglement is simply, in the case of pure states, I'm going to consider many particles that are in a pure state. And it is simply to consider block entropy. You take a block of qubits and ask how it is entangled with the rest of the qubits. So that's the von Neumann entropy of the block qubits. That's also a good measure of multipartite entanglement. But then there are many blocks you can define. So people have also defined some generalized von Neumann entropies by taking all possible partitions and calculating entropies. Okay, so I think this is just a summary of these things. So if you have a pure state bipartite system of arbitrary dimensions, not just qubits, the von Neumann entropy of the reduced density matrices is good. If you have a mixed state of 2 qubits, then the concurrence measure is good. I'm not going to talk about the residual tangle, so I'll skip that, but there is quite a good measure for pure state of 3 qubits. And pure state of many qubits, multipartite measures such as block entropy, entangle, which actually generalizes concurrence, and the Q measure, which is the average purity, is good as measures of multipartite entanglement. And the monogamy of entanglement is basically the statement that if 2 particles are maximally entangled with each other, they cannot be entangled with any other. So if you take the G at Z state, where no 2 of these qubits are actually entangled, but all 3 are entangled, so they have no monogamous relation at all in that particular state. Okay, so let's take some particular Hamiltonian, a spin Hamiltonian, and see how these measures of entanglement fare for the eigenstates of this Hamiltonian. Now, we have exact results for integrable models. For example, if you take this Icing spin chain, so it's a standard Icing spin chain on an open, there are L of these spins. It's an open chain, and they are interacting via this exchange coupling. And there's an external magnetic field which is tilted in the sense that if you have theta to be 0, then the magnetic field is along the z direction, the direction of the entanglement of the interaction. And then this is just a simple Icing model. However, if the field is transverse to this, so theta is 90 degrees, then this is the famous transverse field Icing model, which is also a solvable model in the sense that you can find integrals of motion or constants of motion, completely solve the problems through some transformation and convert it to some fermion problem, calculate entanglement and so forth. But I'm interested in this full problem of theta equals 0 to 90 degrees from one integrable to the other integrable case, because it's actually quite a complex spectrum, and I would like to ask what happens to entanglement in this regime. So just to summarize, what we have found is that there are direct correlations between quantum chaos markers and entanglement. So to elaborate a bit on that, between 0 and pi by 2, you can find numerically, you can find signatures of quantum chaos, such as the levels will be repelling each other, the energy levels will be repelling each other in a typical fashion. For example, the Wigner distribution will be found in this case for the energy level spacing. So when the energy level spacing is that of as close as possible to the Wigner distribution, entanglement has certain special properties as different from the other things. And in fact, entanglement is large in the case where non-integrability occurs. But again, what do I mean by entanglement? So I'll actually come to that because there are different things. Entanglement between two qubits, multipartite entanglement, and so forth. Okay, so we can also study things, these kinds in stationary states, as well as it's interesting to study things like transport, as we have studied. And in all of these cases where we have found that there is a generation of entanglement, especially multipartite kind, along with a transition to non-integrability, away from non-integrable systems, this is accompanied, of course, by avoided crossings in the energy landscape. So we would like to study more closely, as I said at the beginning, avoided crossings and entanglement. So that will be actually what I will concentrate on in this talk. Okay, so this is just some things about the Hamiltonian, that it's symmetric and so forth. And it's important to desymmetrize the Hamiltonian when you're studying things like avoided crossings. As you know from the classic, there's a theorem of von Neumann and Wigner who say that if you consider the energy levels of a system as a function of a parameter for in a subspace of a reduced symmetry, so you're only looking at a definite symmetries, symmetric subspace, then as you're varying one parameter in a real Hamiltonian, the energy levels will typically not cross. So they will come too close to each other, but they will fly away from each other as they come close by, the so-called avoided crossings. So here is a picture of that. So here is what happens as you vary the tilt angle in this Hamiltonian. So we're going to hold the magnetic field and the interaction J and B constant as one each. We're going to take 10 spins and I think 8 spins in this case, it doesn't really matter, and vary the tilt angle from 0 to pi by 2. As I said, both these things are integrable limits. This is the usual Icing model and there's a lot of degeneracy. Here is a more complicated integrable limit of the transverse field Icing model, but in between is this typical landscape where you have energy levels that are changing as a function of this tilt angle in the spaghetti kind of plot. Now, wherever you think there's a crossing, if you go close to that point, you will find that it is actually an avoided crossing and that they never cross. For example, here is something which is clearly an avoided crossing, but even points which are, pointer is not working, but wherever you think that there is a crossing, it's not really a crossing. Okay, so here's some, as I said, the nearest neighbor spacing distributions, just to indicate to you that actually the transition, when you move away from the transverse field Icing model, introduce a non-transverse tilt is very close to the Poisson, is very close to the Wigner distribution, which you know is obtained for systems that are classically non-integrable systems. And maybe this plot I will I will explain a little bit. So this particular curve here, which is going down, again this is a function of the tilt angle. This curve goes down and then picks up again very sharply at this other integrable point, corresponds to the entanglement between any two qubits. So what we are doing is taking all the possible eigenstates, taking the whole spectrum actually of eigenstates, finding out the entanglement content between any two qubits, and seeing how that is changing as a function of the tilt angle. And what you find is that it decreases from the pure Icing model, I mean without any magnetic field, so to speak, or longitudinal magnetic field. As you tilt it, it's decreasing, and then at the other integrable thing, it increases a little bit. And this is interesting, that if you calculate, on the other hand, the block von Neumann entropy, which is measuring for you the multipartite entanglement, it increases in the non-integrable or chaotic limit, and regime, and sort of reaches a maximum in the non-integrable regime, and then comes down again at this. So these two are the complementary features, like the GHZ states. As the entanglement between the qubits decreases, between any two qubits decreases, the multipartite entanglement actually. So the multipartite entanglement increases as this decreases. Okay, so we want to understand this in a little bit more detail. So if you can zoom in to some of these crossings, here you find this. So this is an energy level which comes, has an avoided crossing with this green level, bounces back like this. Okay, so these are all avoided crossings. There's actually a gap there. So when you look at the Q measure, which is the average purity, which is a measure of multipartite entanglement, you see that there is an exchange of entanglement between, let's look at this purple and green levels, for example. So this green has a higher multipartite. This has almost no multipartite. They have an avoided crossing, and then the purple has very large multipartite and green has very little multipartite. They exchange entanglements, and that's what happens everywhere. Now this is itself not very surprising. And similarly, same thing happens with tangle or the concurrence. What is interesting is that if you looked at what happens at the avoided crossing to the measures of entanglement, you see not only that it's exchanged, but actually that there are these peaks here. So if you look at the peaks carefully, you see this kind of structure. So this is the multipartite entanglement increases, whereas the entanglement between any two qubits actually decreases almost to 0 from a very large value. So it's also been known for some time that there are signatures of entanglement in things like quantum phase transitions. A quantum phase transition is sort of a thermodynamic limit of a avoided crossing. So I think it's interesting that when you go look beyond the ground state into the excited states, there is a whole variety of structures in the spectrum where you already see what one sees in the thermodynamic limit in the case of quantum phase transitions. So in order to understand this kind of behavior a little bit more quantitatively and to model these things, I want to study how a typical state is. How do I look at typical states? How do I look at states in this regime, for example? Now, if a state is actually having some properties of quantum chaos, and then it's what is called a typical state. Its distribution is that of random matrices. And this was a question which was asked, as I found later, by actually a cosmologist, and earlier by a person called Lukin, actually, goes back to 1978. What is the typical subsystem entropy of a random state? So you can ask what is a random state, but it essentially means that you take the Hilbert space of states, and you take every state, you sample every state uniformly, and then you find out what is the subsystem entropy. You ask what is the average subsystem entropy. As it turns out, which is also, as we know, a measure of entanglement in the case of pure states, we know that actually this is a very large number. So what Lubkin found was that the average purity of a density matrix of a random pure state is very small. So he has an n by k system, and this he could prove exactly in 1978, from which he inferred that the entropy of a system, that's the von Neumann entropy of a system, is also nearly maximal, is log n minus something which is of the order of which is actually small. Okay? I'm not sure that I got that thing right, but my next slide would have. So there is a certain, so if you were to ask this question, actually the answer is no. If you take a random state and you ask what is the distribution of the reduced density matrix of this state, what is the eigenvalue distribution of the reduced density matrix of this state, this is known. This is known from work of Seth Lloyd and earlier actually by several people. So from a random matrix theory perspective, this is sort of known already, especially without this trace condition. Anyway, so the trace condition gives you this thing. The eigenvalues of the reduced density matrix, which are the Schmidt coefficients, are actually distributed in this manner. And there are correlations between these, which are characterized by these van der Monde determinants. And then you have these factors which are coming from this. So this is called the Laguerre ensemble. So from this, you can find the typical von Neumann entropy by integrating out this joint probability distribution, integrating lambda I log lambda. What page in 19, I think I have in the next slide. Yes. So Don Page studied this question, and he found that that sort of horrible integral can actually be done exactly with this log and all those things could be done exactly. And just to state his abstract, he states that if a quantum system of a Hilbert space of dimension n into k is in a random pure state, the average entropy of a subsystem of dimension n less than k is conjectured to be this very nice simple formula, and is shown to be of the order of log n minus n by twice k, where n is the smaller of the dimension. And thus he concludes that there is less than 1/2 unit of information on average in the smaller subsystem of a total system in a random pure state. That is, if you give me access to only one subsystem of a bipartite system, how much information can I gain about the full pure state? Practically nothing. This is what it says for it. So it's almost like it's a fully mixed kind of thing, although it is not maximally mixed, but a random state is almost fully like that. So this was later proven by other people, and also we added this little bit of thing recently by showing that the minimum eigenvalue of these the reduced density matrices actually has a nice formula which is simply 1 by n cubed, the average of the minimum. You can also derive the distribution of the minimum and so on, which we did more recently. Why is this interesting? Well, the average, the typical eigenvalue will be going as 1 over n, will be scaling as 1 over n. And that's what leads to the entropy being of the order of log n. But the minimum can be very much smaller, and this in fact is of the order of 1 by n cubed, which actually tells you how different a typical state is from a completely random state where all the eigenvalues are 1 over n. Okay, so this is all just some ideas about a random state. Now, I've been talking only about entanglement in a random state in a bipartite sense, but you can ask what is the entanglement between any two qubits if you were to consider a random state. Exact results are not known in this case. For example, if you were to ask questions about concurrence. But there are some numerical works, for example, Scott and Caves in 2003, when they looked at the quantum Baker's map as a as a system for entangling, they state in that probability to encounter pairwise entanglement between a particular pair of qubits in states with 3, 4, 6, and 8 total qubits is 1. That is, with certainty, a 3-qubit state will have pairwise entanglement, whereas only 75% of pairs of a 75% of 4-qubit states will have pairwise entanglement, and a very small number of 6 and 8 practically nothing, 0. So what does this mean? It again means that typical states have negligible pairwise entanglement and nearly maximum multipartite entanglement. Putting together the results of Page and others and this kind of thing gives us this picture of a typical state. And actually typical states, how do you obtain them? You obtain them by quantizing Hamiltonian systems which are classically chaotic, or actually in the case of, for example, like spin systems which we have studied with the tilted field Icing model, without any classical limit, one would still characterize them as quantum chaotic because they have random matrix characteristics. So we have studied this, and there is how to generate them using kick tops and so forth. There's a recent review by Benenti in the archive which talks about random states and quantum chaos. Okay, so I kind of now come to another thing where I would now like to understand in more detail how to use these random states and other very simple states to see what happens under superpositions to entanglement in multipartite states. So we want to model avoided crossings. We know that avoided crossings are typically superpositions. So let us start with a situation where we superpose two states, one which is a state with only dimers in them. Okay, so let's start with a simple state like this with L qubits, where 1 and 2 is in a Bell state, maximally entangled, 3 and 4 are maximally entangled, and so forth. Okay, so there is pairwise maximal entanglement in this. So this is a very simple state as far as entanglement is concerned. We know exactly what is happening. There is no other entanglement except bipartite entanglement. Now we superpose that with a random state, the typical state. So I would like to think of this as an avoided crossing between a level with a large bipartite entanglement content or 2-qubit entanglement content with a very chaotic state which has already undergone a lot of avoided crossings. A state which has not undergone some avoided crossings, intersecting or rather having an avoided crossing with another state which is undergoing, which is already random looking. Okay? So, and then we would like to ask what happens to the entanglement content between, say, 1 and 2 as we change this mixing parameter theta in this case. So, decide that the random state is just a combination of all possible states, I, all the 2 to the power of L, and this AI are random numbers with the only constraint being that their modulus sum is 1. It's normalized. It's uniformly. So if you do that as a function of this 1 minus p, which is the fraction of the random state. So this is a fraction of the random state. So if the random state is 0, you have very large entanglement content. So I actually normalize it so that now I'm looking at the entanglement between all pairwise. I'm looking at all pairwise, all the qubits, and I'm measuring the tangle, which is the square of the concurrence of this, and I'm normalizing it. So this is the maximum possible. So this is all in the form of 2-qubit entanglement. There is no mixing with the random state. As the random state is increased, it decreases till this point, some 0.6 something, and after which there is no 2-qubit entanglement. That is, we have mixed enough of this random state to completely destroy any 2-qubit entanglement that we actually started with. We started with maximally entangled qubits, and we have destroyed all the entanglement between these by mixing it with this random state. And I superpose on this with many realizations of the number of qubits, 10, 6, and so you can see that they all fall on one curve. So this curve is actually quite easy to understand where it comes from, and is basically the entanglement content of what's called a Werner state. So let's take this state phi, which is a superposition of a dimerized state and a random state. Then one can show that the coherent part of the superposition, which is this thing between the superposition, between the random and the dimerized state, is actually small, is exponentially small in the number of qubits. We can show that explicitly so that this is not important. So then the problem actually reduces to finding out the reduced density matrix for this state here. So if you do that, this is the reduced density matrix for any 2 qubits. So let's just take, this is the dimerized state. Obviously, the reduced density matrix of 1 and 2 is just psi 1, 2, psi 1, 2. So that's what you get here. So we take 2 qubits which belong to the same dimer. Okay? So that's this one here. So that's a Bell state. And if you take a random state and ask what is the reduced density matrix of any 2 qubits, you can show again that to a very good approximation, it is simply the identity by 4. So this is the identity by 4, the completely random state that is mixed with a maximally entangled state. So this is an example of the Werner state, and it is well known and it's quite easy to calculate the concurrence in such a state. And you can show that it is exactly 0 if cos squared theta is greater than 1 by 3. So that is precisely what one sees in this picture here. If it is more than 0.67, this is actually exactly 0. So to summarize, if you superpose a random state with a dimerized state, what one produces are Werner states. And it is possible to destroy the 2-particle entanglements that were present in the dimerized states with a sufficient mixing of the random state. It's also interesting to ask what happens to this destroyed entanglement. And as we talked about earlier also, they get converted to multi-particle entanglement. So it's interesting to calculate a block entropy. So the entropy, the von Neumann entropy of 1/2 of the spins with the other half of the spins is calculated here as a fraction of the random state. Now, if this is 1, it's all random, and this is actually the results of Page. So this should match with the results of Page and others. And this is exactly 0 because there is no multipartite entanglement when it began. So actually, this regime, there is a continuous increase of this entanglement. This is for increasing number of qubits. And we have not studied this question very carefully, but I think that these intermediate regimes will be very interesting also to study things like the distribution of the eigenvalues of the density matrix and so forth. But I just want to point out here one thing. The entanglement content in the 2 qubits were already destroyed at 2 by 3 here. The multipartite entanglement continues to grow. So this means that entanglement is being converted from other, the 2 particles has been destroyed, then probably 3, but we don't know how to actually measure that. We don't have a measure like concurrence and so forth. And till the whole thing is converted into a multipartite entanglement. Okay, so this is my the last kind of case where it's even more simple. So we throw off the random state even and ask what happens if there are 2 dimerized states that are coming together. There's been a lot of work on RVB states, the resonance valence bond kind of states, where there are only dimer contents, and then there are RVB gases, and then entanglement studies have been done on such things. This is probably the simplest of that kind, but I think it's a little bit more detailed. And we can do that, I suppose, in this case. But anyways, it's quite interesting. So if you take two states, psi1 and psi2, both of them are in the form of dimers. So 1 and 2 is in some 2-particle pure state, 3 and 4 is in some other 2-particle pure state, etc. Unlike the previous case, I'm not requiring them to be Bell states or anything like that. They are random 2-particle states. Okay, so they are in some dimerized form of this kind. And therefore, there is concurrence between, say, 1 and 2. For example, if 1 and 2 are in this state, the concurrence is quite simply this combination. There is entanglement between 1 and 2. Now we superpose these two and ask, what is the entanglement content between, say, 1 and 2? Again, one can prove this quite straightforwardly, that the reduced density matrix of 1 and 2 is just a combination of the reduced density matrices, the density matrices corresponding to this pure state, phi 1, 1, 2, and the corresponding phi 2, 1, 2. And what we are neglecting is exponentially small in the number of qubits. So this is quite easy to prove. So then we come to this question of what is the, suppose this has some entanglement, or let's say we measure it through concurrence, and this has some concurrence. What is the concurrence corresponding to this density matrix? And it is known that concurrence is convex. That means that the concurrence of this density matrix is less than or equal to this. Less than or equal to this thing here. So superposing two dimerized states lowers the average pairwise entanglement. Two random states, phi 1 and phi 2, which are two random 2-qubit states, and then combine them in to make a density matrix which is of this form, rho, and found its concurrence. And then we are plotting that as a function of cos square theta. Okay? So that is this fraction p. Then what one sees is that these are the pure states corresponding to the density matrices, the endpoints of p equals 0 and p equals 1, and this is all mixed states, and indeed the concurrence of the mixed state is this thing here, is smaller than the average concurrence of these pure states. Okay? And you see another case, another pair of random states for which this is the concurrence in the density matrix, whereas this is the concurrence, the average concurrence. So it's less than that. So this is the convexity. But what we found surprising was that there was a large number of cases for which the upper bound, namely this average, was exactly the density matrix concurrence of the density matrix. So that means that equality was achieved in these things for a very large number of states. So on superposing two qubit states incoherently, the resulting density matrix was optimally entangled. So this, I think, is a measure of the robustness of concurrence. And so we went to this question of when does this happen and why does this happen? So let's pose this question of incoherently superposing two qubit states, pure states, and asking when is the concurrence in rho equal to the average concurrence in phi 1 and phi 2 in this form. And it turns out that if these are real states, phi 1 and phi 2, then in as much as 28.5% of cases, the concurrence in rho has this property. So it's a very large percentage. And it's not hard to see why this is true, at least following the prescription of Wouters, but we don't have yet a very good geometric idea, for instance, of why this happens. But you can derive an inequality based on these two states. Actually, this should be phi 1 and phi 2 instead of psi 1 and psi 2. So these are these pure states which are being incoherently superposed. If they follow this inequality for 2 qubits, then it is optimally entangled in this sense. So these are, by the way, I mean these are just expectation values of sigma y, right? And this is like the modulus of this is the concurrence in the state psi 1. So this is the concurrence in state psi 2. And this is some kind of cross concurrence, if one may wish, between psi 1 and psi 2. Okay, so this is something which we derive. Then you can ask, similarly, you can now generalize this to ask what happens if you superpose not 2, but 3 or more states. So for example, if you superpose 3 states, then you can show that the concurrence is the maximum possible, that is, it's a linear combination of these things for 5.12% of the cases, and you can derive inequalities for which this is true. And it's interesting that if you take 4 real states and you ask when is the concurrence of this the maximum possible, the answer is not even 1. So while there are positive measures of states for 2 qubit, for a superposition of 2 states and 3 states, when you go to 4 or higher, actually, there is not even 1 realization of real states for which this is true. So I think that these are quite interesting characterizations still of just 2 qubits, but in a different way. So this work was done with the undergraduate student, and we just posted that a few months ago. So I think I have kind of come to the end of my talk. So to summarize, entanglement changes occur at avoided crossings where multipartite entanglement builds up at the cost of pairwise entanglement. And superposition of a random state, so to model this, for example, in one instance, as a superposition of a random state with a dimerized one, it results in converting dimers to Werner states, and that lose entanglement at a critical mixing. And this is also simultaneously accompanied by growing block entanglement. And if you superpose dimerized and dimerized states, they result in a reduction of pairwise entanglement, but almost never in its complete annihilation. So there's a robustness of that. And you can derive analytic criteria for the existence of real states of 2 qubits that, when incoherently superposed, have the largest possible entanglement as a sort of consequence. I thought of that. Okay, I think I have come to the end of my talk. Thank you.